This concept worksheet will help you assess your understanding of circular motion and your ability to solve circular motion problems. Okay, now let's look at the first question. Draw a force vector on the diagram such that it only causes the object to increase in speed. Okay, increase in speed, we only want this velocity to increase in speed. We don't want it to change direction. So therefore, the acceleration must be along this direction, right? So if the acceleration is along this same direction, then it will increase the speed. Right, therefore, from F equals to ma, the force and the A must be same direction. Therefore, the force must be this direction. Okay, so this is the answer. Okay, second part. Draw a force vector that causes it to only change direction. Okay, so you do not want it to change speed at all. So only one change direction. So if you don't want it to change speed at all, you cannot have acceleration along this direction, right? In other words, we cannot have an acceleration, for example, that is in this direction. Because if it's in this direction, then you still have a component here and component here, right? So therefore, we must have something that has no component here at all, right? So if no component here, the only way is for the acceleration to be perpendicular, right? Therefore, the force must be perpendicular to the V, right? That's the answer. Okay, lastly, the force that will both increase speed and change direction. So like I mentioned just now, we have a hint already. If it change a speed only, it is this direction. If it change direction only, it is this direction, right? So you want both, it must be the resultant, right? Therefore, in this case, the force must be along this direction. Okay. Right, let's look at question 2. State the type of motion. So if we have acceleration that is along the same direction of the velocity, parallel, right, and it remains parallel throughout. So this is the questions we are very familiar with in our kinematics and linear motion, or what you learn in secondary school, right? It's always either in the same direction or opposite direction, right? But in whichever case, they are parallel. So those are the linear motion where you apply the 4 equation of motion. Okay. Right, next, acceleration is perpendicular to V, and the direction of the acceleration is always in the same direction. So this should be something familiar with you, right? Remember, if we have acceleration due to gravity, it is always in the same direction, always downwards, right? So we could throw a ball in this direction, right? And it will be like this, right? Okay, so what do we call this? Right? Yes, this is called a projectile motion. Okay, lastly, acceleration is perpendicular and it remains perpendicular throughout. So this is different from the projectile motion, right? Such that because the A is always changing direction and always perpendicular. So no matter what the direction of the velocity is, the A is always perpendicular. So this is what we call circular motion. So you really have to know the difference between these two. Very important, right? So this is the main difference between these two. One, for projectile, the direction of A is always the same. Okay, so in this case, always the same. Whereas in circular motion, direction of A is always perpendicular. Okay, always perpendicular. Okay, let's look at question 3. This is where you learn how to solve problems. So first you have to draw the free body diagram first. Right, if I draw the free body diagram on this block here, right, I can see that it's acted by tension at the angle theta, right, and it's also acted by its weight mg. Okay, so this are the two forces acting on the board. Right, so this is in circular motion. I need to resolve it in two directions. Okay, first let me settle, let's say, the vertical direction. So I can say F net equals to MA. So T cosine theta minus mg equals to MA. Since this is moving in a horizontal circle, so A in the horizontal is 0, so it should be MA 0. So I will get T cosine theta equals to mg. Okay. Now let's look at the horizontal. Right, horizontal, I will fix the direction to be towards the center of the circle. Remember, center of circle is here. Center of circle. So A, this direction should be positive because this is the direction of A. So same thing, F net. Okay, in this case, of course, F net I can just write as centripetal force because the centripetal force is the net force that is towards center of the circle, and A, we call it the AC, which is centripetal acceleration. So in the horizontal, there is only one force in this case, which is P sine theta equals to M. A, C, we can also let it be B squared over R because AC is B squared over R or R omega squared. Okay, so you can use either expression depending on what's given. Okay, next, a plane that is banked, right? If you refer this back to your force conceptual worksheet, you have this question. Now let's draw a free body diagram. Okay, and it will be acted by a lift, and lift is always 90 degrees to the wings. Okay, so the forces acting on this object will be mg and the lift, right? And this angle is theta. Okay, and remember we must identify where the center of circle is. Otherwise, you may resolve in the wrong direction. So center of circle is here, this here, right? So it's in this direction. Right, same thing, I can do the vertical first, upwards. F net equals to 0. Okay, since it's moving in horizontal circle, right? And uniform velocity v. Right, so here will be L cosine theta minus mg equals to 0. So in other words, L cos theta equals to mg. Okay, and in the horizontal direction, we will put the direction towards center of circle as positive. So Fc equals to MAC, right? And therefore it is L sine theta equals to mv squared over r. Okay, why do I use mv squared over r? Because v is given here. Okay. Right, next example. Right, let's draw the forces acting on this. Okay, I will draw it here so that it's easier for you to see. So this is a smooth bank surface, so there is no friction. So only other force is mg and the n. So in other words, I can also represent this way. Okay, and this angle is theta. Okay, why is this theta? Okay, let me show you here again. So this should be theta, and this angle here is 90 minus theta, right? Because this should be 90 degrees, right? And don't forget, this should be 90 degrees. So since this is 90 minus theta, this should be theta. Okay, I hope you are able to see this at first glance from now on. So this is theta, right? So it will be similar to the working in the first two example again, right? So say upward F net equals to 0, right? So n cos theta equals to mg. Okay, so now I should be able to do this pretty fast. Right, and in this case, center of circle is here, right? So center of circle is here. So again, towards center of the circle, FC equals to MAC. Okay, so therefore I will get n sine theta equals to mv squared over r. Again, I did not use n1 omega squared because v is given. Okay, please take note here. Sometimes the student, right, the common mistake is this, right? Instead of resolving vertical and horizontal, some student may resolve in this direction. So they try to resolve mg instead, okay, into mg cos theta here and mg sin theta here. Why is this wrong? Why is this wrong? Right, remember, we must resolve the force towards the center of the circle. And center of the circle is here. So this direction does not point to center of the circle. So it will not be able to give you this FC equals to MAC. Okay, because this is not a centripetal force. So this cannot be applied here. So therefore, you are not able to solve the problem if you resolve in this direction. Okay, therefore, always remember to take note where the center of circle is, and you must resolve along that direction. Okay. Okay, next we'll move on to vertical circle. Okay, let's draw the free body diagram now. This object is at the top of the hump, so it will be acted by a normal reaction on the hump, okay, from the ground, so here N. And of course it has its weight, so mg. Okay. Okay, force equation. Where's the center of the circle? Right, it's here, right? So it will be here. So I must make sure I point towards the center of the circle, call it as positive. So mg minus n equals to mass times centripetal acceleration. Okay, so this should be equals to mv squared over r. Right, so mg minus n equals to mv squared over r. If this is too hard for you to begin, right, so you can always begin with this equation as I have done earlier. Right, downward as positive, so mg is positive, n is upward, so it's negative, then this equals to mac, right? So you can always begin with this step if you are not able to see this right away. Derive the maximum velocity such that the object can complete the circular motion. So if we look at the mathematics, right, if I want v to be maximum, then n must be 0, right? So that this term can be maximum. Okay, so therefore n should be 0. So therefore it will be mg equals to mv squared over r, where v is max, right? And m can cancel, so I can write v max square equals to rg. So v max equals to square root rg. Okay, so this is the answer. Okay, we'll look at more examples to get a hang of it. Okay, now we have a different case. The object is like a roller coaster, so it's beneath the loop. Okay, so move from here and go this way. Okay, this is unlike the case here where like a car moving over the hump. Okay, so I draw a free body diagram, right? In this case, the normal reaction should be downwards. Okay, because it is being pressed by the loop, right? So downwards, and of course there is a mg. Okay, so these two should be in the same direction. I just draw this way so that you can see there are two forces. So center of circle is here, right? Remember, center of circle is here. So I should form downward as positive. Okay, I will start from the beginning again. F net equals to. Okay, so in this case, since I'm already solving centripetal force, so I can just say Fc equals to mac. So downward is positive, so both are downward, so mg plus n equals to mv squared over r. Okay, so this will be the equation. Derive the minimum velocity. Okay, so for v to be minimum, mg cannot be changed. The mass cannot change, the G cannot change, right? So the only thing that can change is M. So for V to be smaller, this whole thing must be small, right? So the smallest is when N equals to 0. So again, N equals to 0, right? Then we get Mg equals to MV minimum square over R, right? Again, right, cancel this, so we get MV square minimum equals to Rg, and therefore V minimum equals to root Rg. Okay, I hope you compare these two examples. Right, you can see the expression is totally the same, but one is maximum, one is minimum. Okay, right, and it's not difficult to understand why. In this case here, if you travel too fast, you will fly over, so you will not follow the path. Okay, so you will not be going through circular motion. So you cannot travel too fast. So there's a maximum speed that you should go, right? Therefore, it's Vmax. Whereas in this case, if you travel too slow, what will happen? If you travel too slow, your speed cannot sustain you to go over, so you may drop down, right? So therefore, this must be a minimum speed in order to cover this, go through a circular motion, right? So therefore, it's V minimum. Okay. All right, let's look at the next one. Okay, this case here, you have to take note now. This is a non-uniform vertical circular motion. Non-uniform means V is not constant. Okay, so this is a string, right? A mass that's tied to a string and being swung in a vertical circular motion. Right, so let's look at the top what happened. Draw the free body diagram. Okay, sorry, just like this. Okay, so of course we have the width of the mass, and in this case it is a string, right? So string should have a tension, and tension is always a pull, so it's away from the body. So these two should form the centripetal force, right? Remember, center of circle is here. Okay, so to form the equation, so right now straight away I should be able to write this. Right, derive the velocity v top. Okay, so okay, now let's call this v top, such that it can complete the circular motion. Okay, so looking at this equation, right, I want to complete this. Okay, so just look at this term. Right, I will answer this question first, whether it's maximum or minimum. Okay, so looking at this expression, mg is constant, cannot be changed. So the only thing can be changed is tension, right? Okay, how tight the string is. So in order, looking at this expression, if t is 0, then this v top will be minimum, right? Okay, so actually it must be v minimum. So in this case, I should tension be 0. So this mg equals to m v top square over r. Right, so same thing again. Right, you can now know this expression, right? Compare this with this again, right? It's always the same expression. Okay, let's look at the case where the mass is at the bottom now. When the mass is at the bottom, okay, the weight is still downwards, okay, but what is the difference now? Tension is upwards now, and center of the circle is here. Okay, so in other words, the tension of the circle is towards the center of the circle. So if I form the equation, okay, let me work step by step in this case. Okay, centripetal force equals to MAC. So upward is positive. Why I choose upward positive? Because center is upwards, okay, it's on top. So T is positive, mg is negative, equals to mv squared over r. Okay, so this will be the equation. Alright, now derive an equation, an expression to show the mathematical relationship between V top and V minus. Okay, and the clue is this: by conservation of energy. Right, so from here, if the ball moves down to this point, right, it must drop in one energy, right? That's right, which is the mgh. Okay, and what is the value of h? Right, it is 2r, right? Okay, so it's mg2r or 2mgr. Okay, so this mg2r, this drop in GPE must be equals to gain in KE, right? So the bottom speed should be higher than the top. So therefore I can write, okay, gain in KE equals to loss in GPE. Okay, so gain in KE is half mass times V bottom square, half mv square, right? There's an expression for KE. This minus the KE at the top, half mv top square, should be equals to 2mgr, right? So this is the expression. Sometimes we may need to use conservation of energy to solve for some unknown. Okay, is it more likely that the string break at the top or at the bottom? Show mathematical reasoning. Right, let's do the mathematical reasoning before we make a conclusion. Right, but intuitively you should guess. Okay, so let's look at the expression again. So I will rewrite the equation for the, okay, so you can see it. For the top, I will have this equation. Okay, and since I am going to compare the tension, right, which string will break, I will make T the subject. Okay, let's call this T top. So this will be equals to mv top square over r minus mg. Okay, then we copy from here for the bottom. So T bottom minus mg equals to mv bottom square over r. Okay, therefore T bottom equals to mv bottom square over r plus mg. Okay, so now we need to compare this equation 1 and equation 2. Okay, first we know that V bottom is already greater than V top, right? Because it gained in KE, right? So the V bottom must be higher. Okay, and so this term is already greater than this term. Okay, and this greater term we plus mg, and the smaller term we minus mg, so it makes T top even smaller, right? So therefore tension bottom must be greater than the tension at the top, right? So the greater the tension, the more likely the string will break, right? So the answer is the string will most likely break at the bottom. Okay, so this is the conclusion. If you think about it, if you swing something, you will experience a tension greater at the bottom than on the top, right? And at the top, sometimes tension can even be zero, okay? And the thing will still go in circle. So there's tension can be very small at the top, whereas the bottom, you will experience a bigger tension. Therefore, it is most likely to break at the bottom. All right? Okay, that's the end of this explanation. Thank you.